All right, pause and copy, pause and copy. I'm sorry, I'll try not to do too much pause and copy this semester. So this one is not so straightforward, but it's the same question. Okay, we're asking, as x approaches 1, what is happening to this guy? Now, I'm going to point something out. We care about what does this fraction approach, okay? The key word is approach. So what is it pointing towards? What is it... what's another? I need my thesaurus. What's it approaching? Okay, we don't care what it is, right? Notice that if I plug in 1, then I will be stuck, 0 over 0. That is not a thing we do or can do. That's not a... Well, so I can't just plug in x is 1. So the point I want to make right now is that I care about what this thing is approaching, not what it is, okay? I don't care about what happens when I plug in 1. I care about what happens when x approaches 1. Okay, it's a subtle distinction. I will repeat it as we go on. Now, solution number 1. As usual, or as before rather, we get our function, we choose some x values that approach 1 from the left and also approach 1 from the right. And we maybe look at this row and look at this row. We could say, looks like limit x goes to 1 of this fraction is going to be 1/2. Okay, it looks like. Okay, this is not, all this stuff here doesn't prove anything. Okay, it just gives us an idea of what's happening. Okay, this is not acceptable as a solution in this class. Solution number 3 will be the optimal one, or the one that's actually accepted. But it does look like we're getting a half here. Okay, solution number 2 is, or would be graphically. I don't know how to graph this thing yet. Okay, later on in the course, we'll be learning how to graph this. So let's return to this later. Because we're kind of we're lacking the skills here to graph this. Solution number 3 is the interesting one. I'm going to try to do direct substitution. I can't do it immediately. I can't do it at the very beginning of my calculation, but if I use some skills from Sec 4, grade 10, I can, what can I do? Well, I can factor. That is a difference of squares. It becomes x minus 1, x plus 1. Now, x is approaching 1. X does not equal 1. That's an important thing to note right now, because if I want to cancel, I do want to go boop, boop, I want to cancel those, right? If I want to do that, I need to know that x is not equal to 1, but that's guaranteed by the idea of a limit. Okay, as I said before, in a limit we have x approaching 1. We don't have x equal to 1. We have x approaching 1. Okay, for that reason I can do this cancellation. And I get 1 over x plus 1. And now I've taken my strange situation. This was a strange situation up here. Okay, this original limits, this was of the form 0 over 0. Okay, because when you plug in x equals 1, you get 0 over 0. So this is a very strange thing. Now, with this cancellation, and with the factoring that preceded it, I have removed the weirdness. The weirdness is gone. And now I can do my direct substitution. So if you want, you can put a little ds here to indicate to your reader that you are doing a direct substitution. So this x here is being replaced with 1, and I get 1 over 2. Okay, so this is the solution we want here. Okay, we want to do these things, you could say algebraically. So you want to not use table of values, not use a picture, but use some kind of techniques that you learned in high school to resolve this nicely. Okay, this solution says let's say from this we see that our function when I do the factor and cancel, it's going to equal to 1 over x plus 1 as long as x is not equal to 1. Now, this function here I can graph this. Okay, this is simple enough that I can do it more or less from memory. Not from memory, it's a hyperbola. I think it's sometimes taught in high school. But I can graph that. Oops. Let's go. Black set of axes. Bear with me here. Now it's going to be at, let's say, -1. It's going to be this vertical line that my graph approaches. So if this is +1 here, this will be -1 here. Now I know that when x goes to 1, the y values go to 1/2. So I can find that point, which would be, I'm getting very scrunchy here. So when x is 1, y is 1/2. That is this point right about here. So I know that the function is going to do something like this. That's kind of hyperbola. And we get, yeah, it's going to go like that. So we'll do more of this later on in the course. Don't worry if you don't remember graphing these. So this is the graph of y is equal to 1 over x plus 1. Now, if I want to get the function f, I have to modify this a little bit. So here we have the function y that I just graphed. Here's the function f. Now they're the same as long as x is not equal to 1. Now when x equals 1, this function does not exist. Okay, if you try to plug x equals 1 in here, you get 0 over 0. Try that on your calculator, no luck. So what we can do here is just put a little, oopsie daisy. Just put a little, what we're going to do is put a little hole here to indicate that the function just doesn't exist there. So the graph of the function f is the same as this one, except that when x is equal to 1, it doesn't exist. Got a little hole there. So now I'll relabel this as f of x is equal to x minus 1 over x squared minus 1. Okay. So don't worry about the graphing. We will do a whole week or two of graphing later in the course. But for now, let's focus on this graph. And the limit we're talking about is as x goes to 1. Now that means we're going like that, and we're going like that. So these limits are approaching this hole, right? But they never get there. Okay, this is one thing I want to kind of emphasize, is that limit x goes to 1 of this function equals a half. Okay, that's what we found above. And this is despite, this is even though f of 1 does not exist. Okay, so this is the difference between what a limit is and what it means to just plug in 1 into a function. Okay, with a limit we care about what we're approaching. Okay, looking at these arrows, I can see when x approaches 1, the y values do approach a half here. But the function itself doesn't exist. Or you could put it this way, you could say the function approaches a half, but it never gets there, right? It never gets there, but we don't care. For a limit, we don't care. Okay. Now, these limits we've done so far, limit x goes to 2 of x cubed, and limit x goes to 1 of x minus 1. Now, I've mentioned this before, but I want to emphasize it. These are called two-sided limits. They're called two-sided limits because, here, for the first one, as I showed you earlier, you have 2 here, and I can approach 2 from 2 different directions. Okay, so this 2 here is referring to the 2 sides here. And likewise, for this one, I can approach 1 from 2 different directions. So we give them the name two-sided limits. So I guess you'd say the default, this is usually the default limit, is a two-sided limit. And later on we'll see a one-sided limit.